I am from Spain, and I am doing my PhD in Universidad Complutense de Madrid, and my work focuses in photonic crystal fibers with liquid crystals. Photonic crystal fiber is a photonic crystal in two-dimensional. It's like a standard fiber with cavities inside. These cavities are in the beginning empty, and you can fill the cavities with some gases or liquids or whatever.
Hey David, you have to confirm it. Once you apply that, after that you have 15 seconds to confirm it. Aplicar.
No, aplicar?
Yeah. Yeah.
I can do that.
You have to confirm it after. If there is some variable part somewhere you have to confirm it.
No. It's the same. You know? My computer is a little bit, yes. Thanks. There are mainly two different types of photonic crystal fibers. The first one has the core solid, and the second one has the core hollow. In the first one, my work is focused in the first one. The mechanism of getting the light is the same as a normal standard fiber. It's modified total internal reflection. In the second one, the fibers are empty, and the core are hollow, and the mechanisms are by photonic band gap. The photonic band gap, as you know, there are some wavelengths that can be guided and some wavelengths that cannot. In my work, I have my research is focused with the first one because it's easier for my purpose. This type of guide of photonic crystal fiber is polarization maintained guide. This fiber has the core solid and has two wider cavities that maintains the polarization. I have made two different types of interferometers, and in the first one I have the liquid crystal in the surroundings, and in the second one I have filled only the two wider cavities of the polarization maintaining fiber. The alignment of the molecules of the liquid crystal inside, the easy way is the homogeneous alignment. This is the first one. Is the liquid crystal flows into the cavity, and when you apply a voltage, the crystal liquid molecules changes its orientation and becomes perpendicular to the fiber. The last one is the homeotropic alignment, in which exists a singularity in the middle, in which appears a third-dimension skate. This one, I don't know how to achieve this goal, but in the future I can try. My devices are mass tender interferometers. That means that I have fused two pigtailed standard fibers, in which in the first point, in this point, the core mode couples part of his energy to the cladding modes, and becomes there are two paths in the inner and in the cladding. And the second point, the two components of the light couples one more time and becomes an interferometer. In my fibers, in the middle, there are two wide cavities, two wider cavities. That means that I have two interferometers, each interferometer in each direction of the polarization. One in the parallel to the plane of the two wider cavities, and the other in the perpendicular to these cavities. Here in the photo, we can see the spacing points of the two interferometers. In this one, the two widest cavities are filled with liquid crystal, and the spacing point must be with a very low electric arc, because if not, if the arc is higher, becomes appears bubbles, and with bubbles we cannot accumulate light. In the second one, in this, the fiber is empty and the splicing point is perfect. You can see how the smaller cavities are collapsed and only remains the two wider. That is to do. The point, the splicing point is somewhere in this point. The first one, this is the interferometer that has a liquid crystal in the surroundings. No inner, in the surroundings only. We can see in this graph how the length of the interferometers becomes to appears. The pattern is lower when the length is higher. Here we can see two different interferometers with two lengths, and there we can see how when we apply voltage, the maximums of the pattern becomes higher. In this case, we have launched circular polarized light. I have tried to launch different polarization of light with linearly polarization, because how this fiber is polarization maintained, it depends in the polarization. But as the standard fiber, this is the standard fiber. In the starting point, I can assure that the direction of the alignment of the polarization is one direction determined. But when the light becomes in this point, I cannot assure if it's linear or circular or whatever, and it's very sensitive. The second interferometer that is this, we can see how the two weather cavities are filled with liquid crystal. You can see between the cross polarizers. These kind of interferometer are much sensitive than the first, and is much more interesting. We can see the blue pattern, how is the pattern without voltage, and when we apply voltage, the pattern changes very easily. If the voltage is enough, appears two band gaps or three. That is because as we have two different directions, in one direction, the mechanism of guidance is by total internal reflection, and in the other direction is by photonic band gap. And just if we apply more voltage, appears the band gaps. And I have these interferometers I did 1 week before come here, and I have no time to do the analytical work. But as I saw, it's very. I have manufactured two different types of interferometers that can be improved by changing the parameters, the different types of liquid crystals and different types of photonic crystal fibers. And that's all.
How large are the microcavities in
the whole large, the diameter, yeah, the wider 4.4 microns, and the smaller 2 microns.
Okay, thank you again.